NiFi Architecture. Here you can see an architectural diagram of NiFi. Apache NiFi is a software project from Apache Software Foundation designed to automate the flow of data between software systems. Leveraging the concept of extract, transform, load, it is based on the Niagara files software previously developed by the US National Security Agency NSA, which is also the source of a part of its present name NiFi. It was open sourced as a part of NSA's technology transfer program in 2014. NiFi is also able to operate within a cluster. Starting with the NiFi 1.0 release, a zero leader clustering paradigm is employed. Each node in a NiFi cluster performs the same task on the data, but each operates on a different set of data. Apache Zookeeper elects a single node as the cluster coordinator, and failover is handled automatically by Zookeeper. All cluster nodes report heartbeat and status information to the cluster coordinator. The cluster coordinator is responsible for disconnecting and connecting nodes. Additionally, every cluster has one primary node, also elected by Zookeeper. As a data flow manager, you can interact with the NiFi cluster through the user interface UI of any node. Any change you make is replicated to all nodes in the cluster, allowing for multiple entry points. Now we are focusing on OS hosts. NiFi executes within a JVM on a host operating system. There are three repositories that are utilized by NiFi. Each exists within the OS host's file system and provide specific functionality. As an example, we can consider Linux. NiFi supports operating systems like Linux, Unix, Windows, and Mac OS. As an example too, we can consider NiFi.web.https.host. This signifies the HTTP host. Default value is 127.0.0.1. This is in the NiFi.properties file. As an error example, we can consider this one. Error NiFi logging handler org.apache.nifi.stderr open JDK 64-bit server VM warning. If the number of processors is expected to increase from 1, then you should configure the number of parallel GC threads appropriately using -xx:parallel GC threads equal n. Now we are focusing on JVM. NiFi executes within a JVM on a host operating system. NiFi lives within the JVM and is thus limited to the memory space it is afforded by the JVM. JVM garbage collection becomes a very important factor to both restriction the total practical heap size as well as optimizing how well the application runs over time. NiFi jobs can be I/O intensive when reading the same content regularly. Configure a large enough disk to optimize performance. As an example, we can consider this under Kerberizing embedded Zookeeper Server. java.arc.15 equal dash djava.security.auth.logging.config equal dot /config/ zookeeper dash jaas.com conf. We need to tell NiFi to use this as our JAAS configuration. This is done by setting JVM system properties. So we will edit the conf/bootstrap.conf file. If the client has already been configured to use Kerberos, this is not necessary as it was done above. Otherwise, we will add this line to our bootstrap.conf file. As an example too, we can consider this one, this bootstrap property java.arc.n. Any number of JVM arguments can be passed to the NiFi JVM when the process is started. These arguments are defined by adding properties to bootstrap.conf that begin with java.arg. The rest of the property name is not relevant other than to differentiate property names and will be ignored. The default includes properties for minimum and maximum Java heap size, the garbage collector to use, Java IO temporary directory, etc. The bootstrap.conf file in the conf directory allows users to configure settings for how NiFi should be started. This includes parameters such as the size of Java heap, what Java command to run, and Java system properties. As an example 3, we can consider the step to increase the maximum amount of memory for the JVM. Step 1, open the Apache NiFi installation directory. Step 2, open the file bootstrap.conf in conf directory in text editor. Step 3, find the line java.arc.3 equal dash X MX 512 M. Step 4, increase the maximum amount of memory available to the JVM. For example, java.arc.3 equal dash xmx 2048 M. You can configure Apache NiFi to suit your needs by following the Apache NiFi documentation. Here, Micro Focus recommends making these configuration changes here, and with regarding Java virtual machine memory, Micro Focus recommends that you increase the maximum amount of memory that can be used by the Java virtual machine JVM. As an error example, we can consider this: fail to drop flow files due to java.lang.illegal state exception. Cannot update repository because all partitions are unstable. Partition are unusable at this time. Writing to the repository would cause corruption. This most often happens as a result of the repository running out of disk space or the JVM running out of memory. Now we are focusing on web server. The purpose of the web server is to host NiFi's HTTP based command and control API. As an example, we can consider this. This will be a very simple REST API that exposes a single endpoint get /API. This endpoint returns a 200 OK response with a small piece of JSON that changes based on the value of a URL parameter param1. Any other path or method will return 404. First, we need a web server that accepts HTTP request. For this, we can use the handle HTTP request processor. Behind the scenes, this includes a Jetty web server. At the handle HTTP request and double click it to enter the config window. You can customize the port it listens to. The port it listen on, but I will leave it at the default 80. You must add and enable HTTP context map. Simply select create new service, then from the drop down and create a new one with the default settings, then enabled it. Next is allowed paths that control which path the API will respond to. This is regex pattern, so can include many paths, but in my case I am only allowing one /API. Lastly, set all methods except get to false. Example, allow post, allow put, etc. That's all we need to accept HTTP request and hit apply. As an example, we can consider this. NiFi provides several different configuration options for security purposes. The most important properties are those under security properties, heading in the NiFi.properties file. Once the above properties has been configured, we can enable the user interface to be accessed over HTTPS instead of HTTP. This is accomplished by setting the nifi.web.https.host and nifi.web.https port properties. The nifi.web.https host property indicates which hostname the server should run on. If it is desired that the HTTPS interface be accessible from all network interfaces, a value of 0.0.0.0 should be used. To allow admins to configure the application to run only on specific network interfaces, nifi.web.http.network.interface * or nifi.web.https.network.interface * properties can be specified. It is important when enabling HTTPS that the nifi.web.http.port property be unset. NiFi only supports running on HTTP or HTTPS, not both simultaneously. NiFi's web server will require certificate-based client authentication for users accessing the user interface when not configured with an alternative authentication mechanism, which would require one-way SSL, for instance, LDAP, OpenID Connect, etc. Enabling an alternative authentication mechanism will configure the web server to want certificate-based client authentication. This will allow it to support users with certificates and those without that may be logging in with credentials. As an error example, we can consider this error NiFi logging handler org.apache.nifi.sdd err failed to start web server, unresolved address. Now we are focusing on flow controller. The flow controller is the brains of the operation. It provides threads for extensions to run on and manages the schedule of when extension received resources to execute. The flow controller maintains the knowledge of how processes connect and manages the threads and allocates thereof which all processes use. The flow controller acts as a broker, facilitating the exchange of flow files between processors. Here you can see an AWS credentials service provide context to two processors. The flow controller is the glue that brings everything together. It allocates and manages threads for processors. It's what executes the data flow. Also, the flow controller makes it possible to add controller services. Those services facilitate the management of shared resources like database connections and cloud services provider credentials. Controller services are daemons. They run in the background and provide configuration, resources, and parameters for processors to execute. For example, you may use AWS credentials provider service to make it possible for your services to interact with S3 buckets without having to worry about credentials at the processor level. Just like with processors, a multitude of controller services is available out of box. As an example, we can consider this property in NiFi.properties file. NiFi.h2.url.append. This property specifies additional arguments to add to the connection string for the H2 database. The default value should be used and should not be changed. It is lock underscore timeout equal 25,000 and write underscore delay equal 0 and auto underscore server equal false. As an error example, we can consider this error occurred in NiFi under NiFi 1.7.1 release build cluster of 3 nodes. Other nodes for Zookeeper, Java 1.8 build 181. The error is error NiFi logging handler org.apache.nifi.std err failed to start web server, unable to start flow controller. Now we are focusing on processor 1. Processors actually perform the work. In terms, a processor is doing some combination of data routing, transformation, or mediation between systems. Processors have access to attributes of a given flow file and its content stream. Processors can operate on 0 or more flow files in a given unit of work and either commit that work or roll back. Here you can see an example of uploading files from SFTP server to HDFS. NiFi uses a web interface to create a data flow. The analyst who recently started working with Hadoop, the developer and bearded admin will cope with it. The last two can interact only with rectangles and arrows, but also with REST API for collecting statistics, monitoring, and managing data for components. Here I will show a few data flow one data flow example with some common operations. In this example, the list SFTP processor lists files on a remote server. And the Result of this listing is used for parallel downloading of files by all the nodes of the cluster by the fetch SFTP processor. After this, attributes are added to each file obtained by passing its name, which then are used by the put HDFS processor when writing the file to the final directory. Here you can see a list. SFTP is connected with test2. Test2 is connected to NiFi Flow, and here input is connected with queued, and queued 0 is connected to fetch SFTP, and fetched FSTP is connected with the permission denied not underscore f4, and it is connected to log attribute, and fetch SFTP is connected with comments.failure, and comments.failure is connected to fetch SFTP, and fetch SFTP is connected with success, and success is connected to update attribute. Update attribute is connected with success, and success is connected to put HDFS. Here you can see anatomy of a processor. NiFi provides a significant amount of information about each processor on the canvas. This diagram shows the anatomy of a processor. This has the number of elements. Processor type. NiFi provides several different types of processors in order to allow for a wide range of tasks to be performed. Each type of processor is designed to perform one specific task. The processor type put file in this example describes the task that this processor performs. In this case, the processor writes a flow file to the disk or puts a flow file to a file. Bulleting indicator. When a processor logs that some event has occurred, it generates a bulletin to notify those who are monitoring NiFi via the user interface. The DFM is able to configure which bulletins should be displayed in the user interface by updating the bulletin level field in the settings tab of the processor configuration dialog. The default value is warn, which means that only warnings and errors will be displayed in the UI. This icon is not present unless a bulletin exists for this processor. When it is present, hovering over the icon with the mouse will provide a tooltip explaining the message provided by the processor as well as the bulletin level. If the instance of NiFi is clustered, it will also show the node that emitted the bulletin. Bulletins automatically expire after 5 minutes. Status indicator. This shows the current status of the processor. The indicators, the possible indicators are running. The processor is currently running, and stopped. The process is valid and enabled, but is not running. Invalid. The processor is enabled but is not currently valid and cannot be started. Hovering over this icon will provide the tooltip indicating why the process is not valid. And disabled. The process is not running and cannot be started until it has been enabled. This status does not indicate whether or not the process is valid. Here you can see running state, running status indicator here. Processor name. This is the user defined name of the processor. By default, the name of the processor is the same as the processor type. In this example, the value is copy to /review. Active tasks. The number of tasks that this processor is currently executing. This number is constrained by the concurrent task settings in the scheduling tab of the processor configuration dialog. Here we can see that the processor is currently performing one task. If the NiFi instance is clustered, this value represents the number of tasks that are currently executing across all the nodes in the cluster. 5-minute statistics. The processor shows several different statistics in a tabular form. Each of these statistics represent the amount of work that has been performed in the past 5 minutes. If NiFi instance is clustered, these values indicate how much work has been done by all the nodes combined in the past 5 minutes. These metrics are in the amount of data that the processor has pulled from the queue of its incoming connections. This value is represented as count and size, where count is the number of flow files that have been pulled from the queue, and size is the total size of those flow files content. In this example, the processor is just pulled 29 flow files from the input queues for total of 14.16 megabytes. Read write. The total of the flow file content that the processor has read from the disk and written to disk. This provides valuable information about the I/O performance that this processor requires. Some processors may only read the data without writing anything, while some will not read the data but will only write data. Others will never read nor write data, and some processors will both read and write data. In this example, uh, we see that in the past 5 minutes the processor has read 4.88 MB of the FlowFile content and has written 4.88 MB as well. This is what we would expect, since this processor simply copies the content of the flow file to the disk. Note, however, this is not the same as the amount of data that pulled from the input queues. This is because some of the files that it pulls from the input queues already exist in the output directory, and the processor is configured to route flow files to failure when it occurs. Therefore, for those files which already existed in the output directory, data was neither read nor written to disks. Out. The amount of data that processor has transformed to its outbound connections. This does not include flow files that the processor removed itself, or flow files that are routed to connections that are auto-terminated. Like in metric above, this value is represented as count, where count is the number of flow files that have been transferred to outbound connections, and size is the total size of those flow files content. In this example, all of the relationships are configured to be auto-terminated, so no flow files are reported as having been transferred out. Tasks time. The number of times that this processor has been triggered to run in the past 5 minutes, and the amount of time taken to perform these tasks. The format of the time is hour, minutes, and seconds. Note that the amount of time taken can exceeded 5 minutes, because many tasks can be executed in parallel. For instance, if a processor is scheduled to run with 60 concurrent tasks, and each of these tasks takes 1 second to complete, it is possible that 60 tasks will be completed in a single second. However, in this case, we will see the time metric showing that it took 60 seconds instead of 1 second. This time can be thought of as system time, or said another way, this value is 60 seconds because that's the amount of time that would have taken to perform action if only a single concurrent task were used. And here you can see a processor. Here you can see a status symbol, processor name, processor type, 5 minute statistics, bulletin indicator, and active tasks. We can consider this as an example here. Validating processor properties. A processor is not able to be started if its configuration is not valid. Validation of a processor property can be achieved by setting validator on the property descriptor, or by restriction allowable values for the property via the property description, property descriptor dot builders allowable values method, or identifies control service method. In addition, if a property is dependent on another property by means of the property descriptor dot builders depends on method, and the dependency is not satisfied, then the property will be validated. For example, we can consider these two property descriptors. In this case, if the use file property is set to true, then the processor will not be valid unless file to use property is set to a valid file name. If the use file is set to true and file to use does not have a value set, the processor will be invalid because file to use property is required. If use file is set to true and the file to use has a value set by the value set, but the specified file does not exist, the processor will also be invalid because the file to use property is invalid according to the validator. However, if the use file property is set to false, then the file to use property is said to have a dependency that is not satisfied. As a result, the file to use property will not be considered in the validation. Therefore, if the use file is set to false and file to use has no value set, the processor will still be valid even though file to use is required. It is only required if the file use file is true. Likewise, if file to use is set to non-existent file name such as /file /that /does /not /exist, the processor will still be valid as long as use file property is set to false. Furthermore, the file to use property will not be shown in the NiFi UI unless use file is set to false. There are times though when validating a processor properties individually is not sufficient. For this purpose, an abstract processor exposes a custom validate method. As an example too, we can consider this code segment. Here you can see this trick class is extending abstract processor and it's overriding on trigger method here. As an error example, we can consider this one, this exception. As an exception example, we can consider this one. Process exception indicates an issue occurred in user code while processing a flow file. In this tab contains several different configuration items. First, it allows the DFM to change the name of the processor. The name of a processor by default is the name is the same as the processor type. Next to the processor name is a checkbox indicating whether the processor is enabled. When a processor is added to the canvas, it is enabled. If the processor is disabled, it cannot be started. The disabled state is used to indicate that when a group of processors are started, when such as when DFM starts an entire process group, this disabled processor should be excluded. Below the name configuration, the processor's unique identifier is displayed along with the processor's type. And NAR bundle. These values cannot be modified. Next are two dialogues for configuring penalty duration and yield duration. During the normal course of processing a piece of data, a flow file, an event may occur that indicates that the data cannot be processed at this time, but the data may be processable at a later time. When this occurs, the processor may choose to penalize the flow file. This will prevent the flow file from being processed for some period of time. For example, if the processor is to push the data to a remote service, but the remote service already has a file with the same name as a file name that processor is specifying, the processor may penalize the flow file. Penalty duration allows the DFM to specify how long the flow file should be penalized. The default value is 30 seconds. Similarly, the processor may determine that some situation exists such that the processor can no longer make any progress, regardless of the data that is processing. For example, if a processor is to push data to a remote service and that service is not responding, the processor cannot make any progress. As a result, processor should yield, which will prevent the processor from being scheduled to run some period of time. That period of time is specified by setting the yield duration. The default value is 1 second. The last configuration option on the left hand side of settings tab is the bulleting level. Whenever the processor writes to its log, the processor will generate a bulletin. These settings indicate the lowest level of bulletin that should be shown in the user interface. By default, the bulletin level is set to 1, which means that it will display all warning and error level bulletins. The right hand side of the settings tab contains an automatically terminate relationships section. Each of the relationships that is defined by the processor is listed here along with its description. In order for a processor to be considered valid and able to run, each relationship defined by the processor must be either connected to a downstream component or auto-terminated. If a relationship is auto-terminated, any flow file that is routed to the relationship will be removed from the flow and its processing considered complete. Any relationship that is already connected to downstream component cannot be auto-terminated. The relationship must first be removed from any connection that uses it. Additionally, for any relationship that is selected to be auto-terminated, the auto-termination status will be cleared, turned off if the relationship is added to the connection. And you can also see scheduling tab. And properties and commands. So in summary, as an array example, you can see here this. We can consider this one. Error failed to put a standard flow file recording here. And other information are here. Now we are considering extension N. There are various types of NiFi extensions which are described in other documents. The key point here is that extensions operate and execute within JVM. NiFi is at its core built for extension, and as such it is a platform on which data flow processors can execute and interact in a predictable and repeatable manner. Points of execution include processors, controller services, reporting tasks, prioritizers, and customer user. As an example, we can consider this: create your UI, build and bundle var in your processor NAR. Step 2, the var need to contain a NiFi processor configuration file in the meta-inf directory which associate the custom UI with that processor. Place the NAR in the lib directory and it will be discovered when NiFi starts up. Step 4, in the configuration processor window for the processor, the properties tab should now have an advanced button which will access the custom UI. To add a custom UI to a processor, the content of the ni-processor-configuration as follows: Apache org.apache.nifi.processors.attributes.update attributes $$ and then project.group id NiFi-update-attribute-nar and again you have to give a project.version information. Custom UIs can also be implemented for controller services. And as an example, see example 2, we can consider this one, the use of org.apache.nifi.ui.extension.ui extension in project NiFi by Apache. Here you can see the method populate remaining controller service content in the class controller service resource. Here this will populate the URIs for the specified controller service. The code, the steps are here. As an example 3, we can consider this one, this property in NiFi-registry.properties file. This NiFi.registry.extension.dir1, the full path on the file system to the location of the jars for the given. As an error example, we can consider this one occurred in building custom NiFi processor with controller service. Error could not generate extensions documentation. org.apache.maven.plugin.mojo execution exception failed to create extension documentation at org.apache.nifi.namojo.generate documentation at org.apache.nifi.namojo.execute. Now we are focusing on FlowFile Repository. The FlowFile Repository is where NiFi keeps tracks of the state of what it knows about a given flow file that is presently active in the flow. The implementation of the repository is pluggable. The default approach is a persistent write-ahead log located on a specified disk partition. Here you can see pass-by reference. An important aspect of flow-based programming is the idea of resource constraint relationships between the black boxes. In NiFi, these are queues and processors respectively. Flow files are routed from one processor to another through queues simply by passing a reference to the flow file, similar to the claim check pattern in EIP. In the web crawler flow here, in Invoke HTTP processor reaches out to the URL with an HTTP GET request and adds the status code attribute to the flow file depending on what the response was from the HTTP server. After updating the flow file's file name in the update attribute processor after invoke HTTP, there is a root on attribute processor that routes flow files with the successful status code attributes to different processors. Those that are unmatched are dropped by the root on attribute processor because it is configured to auto terminate any data that does not match any of the routing rules. Coming into the root on attribute processor, there is a flow file F1 that contains the status code attribute and points to the content C1. There is a provenance event that points to C1 and include a snapshot of F1 but is omitted to better focus on the routing. This information is located in the flow file content and provenance repos respectively. After the routing root on attribute, processor examines the flow file status code attribute. It determines that should be routed to two different locations. First thing that happens is the processor clones the flow file to create F2. This copies all of the attributes and the pointer to the content. Since it is merely routing and analyzing the attributes, the content does not change. The flow files are then added to the respective connection queue to wait for the next processor to retrieve them for the provenance reported documents the change that occurred, which include the clone and two root events. Each of these events has a pointer to the relevant content and contains a copy of the respective flow files in the form of snapshot. Here you can see update update attributes. Process is connected with success, and success is connected to pass root on attribute. Root on attribute is interact with Q0. Here Q, and this Q is connected to remove duplicate in detect duplicate process, and root on attributes interact with Q here, and Q is connected to log attribute here, and in before F1 is connected to F. Basically, F1 is pointing to C1 in flow file, and here in the content you can see C1, and in after update attributes interact with Q, and Q is connected to root on attribute here, and root on attribute interacts with Q, and Q is connected to detect duplicate here, and pass root on attributes interact with Q here, and Q is connected to log attributes, and here in the FlowFile repository F1 is pointing to C1, and F2 is pointing to the C1 here, and in the content repository you can see C1 here, and in provenance in clone P1 is pointing to F2, and in root P2 is pointing to F1, and in root P3 is pointing to F2. Here you can see the FlowFile repository contains metadata about the files currently in the flow. NiFi claims to be reliable. How is it in practice? The attributes of all the flow files currently in use, as well as the reference to their content, are stored in FlowFile repository. At every step of the pipeline, modification to a flow file is first recorded in the FlowFile repository in a write ahead log before it. For each flow file that currently exists in the system, the FlowFile repository stores the flow file attributes, pointer to the content of the flow file located in the FlowFile repository, state of the state of the flow file, for example, to which queue does the flow file belongs at this instant. The FlowFile repository gives us the most current state of the flow, thus it's a powerful tool to recover from an outage. NiFi provides another tool to track the complete history of all the flow files in the flow. The provenance. As an example, we can consider the interface FlowFile repository. Implementations must be as an example, we can consider as an exception example, we can consider this exception occurred in initialize method in interface FlowFile repository here. IO exception, and it's if it is unable to initialize the repository. As an example too, we can consider commit. When the commit method is called, the flow file's new state is persistent in the FlowFile repository, and any provenance events that occurred are persisted in the provenance repository. The previous content is destroyed unless another flow file references the same piece of content, and the flow files are referred to the outbound queues so that the next processors can operate on the data. Here commits the current session, ensuring all operations against flow files within these sessions are atomically persisted. All flow files operated on within this session must be accounted for by transfer or removal of, or the commit will fail. This method is available in the interface process. As an error example, as an exception example 2, we can consider this one, flow file handling exception. If not all flow files acted upon within this session are accounted for by user code such that they have a transfer identified or were marked for removal, automated rollback occurs. This exception can occur in commit method in interface process. As an example 2, we can example 3, we can consider property NiFi.flowfile.repository.implementation. The FlowFile repository implementation, the default value is org.apache.nifi.controller.repository.write ahead FlowFile repository. The other current options are org.apache.nifi.controller.repository.volatile FlowFile repository, and org.apache.nifi.controller.repository.rocksdb FlowFile Repository. This property is available in NiFi.properties file. As an error example, we can consider this FlowFile Repository. Now we are focusing on content repository. The content repository is where the actual content bytes of a given flow file live. The implementation of the repository is pluggable. The default approach is a fairly simple mechanism which stores blocks of data in the flow system. More than one file system storage location can be specified so as to get different physical partitions engaged to reduce contention on any single volume. Here you can see copy on write. In this example, we are focusing on the compress content processor of the template that compresses bundle of merged flow files containing web pages that were queued. In this example, the content C1 for flow file F1 is being compressed in the compress content processor. Since C1 is immutable and we want a full replayable provenance history, we can't just overwrite C1. In order to modify C1, we do a copy on write, which we accomplish by modifying the content as it is copied to a new location within the content repository. When doing so, the flow file F1 is updated to point to a new content C2, and a new provenance event P2 is created, referring to a new flow file F1.1. Because flow file repo is immutable, instead of modifying old F1, the new delta F1.1 is created. Previous provenance events still have the pointer to the C1 to the content C1 and contain all attributes, but they are not the most up-to-date version of the flow file. For the sake of focusing on copy on write event, the flow file F1 flow file F1's provenance events leading up to this point are omitted here. Here you can see before success is connected to compress content, and it's interact with success, and F1 is pointing to C1 in flow file, and in content you can see C1. In after success is connected to compress content, and it's interact with success, and in FlowFile repository you can see the F1 is pointed to C1 is there, and now new one, new F1.1 is pointing to C2, and in the content repository this C1 is the plain text, and here C2 is compressed, and in provenance here P2 is pointing to F1.1. it's in the modify. Here you can see copy on write in NiFi. The original content is still present in the repository after flow. In this example, consider a processor that compresses the content of the flow file. The original contents remains in the content repository, and a new entry is created for compressed content. The content repository finally returns a reference to the compressed content, and the flow file is updated to point to the compressed data. This drawing sums up the sums up the example with the processor that compresses content of flow file. Here you can see processor is connected to content repository, and in content repository original content is connected to compressed content is moved to content original content is connected to compressed content on copy on write here, and compressed content is connected to process. Here you can see that content repository has 35% of its disk consumed by content claims that are tied to flow files still active somewhere in one or more data flows on the NiFi canvas. This leaves 15% of the disk space to be used for archived content claims. There are three properties in the NiFi.properties file that deal with archiving on content in the NiFi content repository. The default NiFi values are NiFi.content.repository.archive.max.retention.period equal 12 hours. NiFi.content.repository.archive.max.usage.percentage 50%. NiFi.content.repository.archive.enabled equal true. Purpose of content archiving is so that users can view and or replay content via the provenance UI that is no longer in the data flows. The configured values do not have any impact on the amount provenance history that is retained. If the content associated to a particular provenance event no longer exists in the content archive, provenance will simply report to the user that content is not available. The content archive is kept within the same directory or directories where you have configured your content repositories to exist. When a content claim is archived, that claim is moved into an archive subdirectory within the same disk partition where it originally existed. This keeps archiving from affecting NiFi's content repository performance with unnecessary writes that would be associated with moving archived files to a new disk partition, for example. The configured max retention period tells NiFi how long to keep archived content claim before purging it from the content archive directory. The configured max usage percentage tells NiFi at what point it should start purging archived content claims to keep the overall disk usage at or below the configured percentage. This is a soft limit. Let's say the content repository is at 49% usage. The 4 GB content claim then becomes eligible for archiving. Once at time this content claim is archived, the usage may exceed the configured 50% threshold. At the next checkpoint, NiFi will remove the oldest archived content claims to bring the overall disk usage back or below 50%. So this value should never be set to 100%. These two properties are enforced using an or policy. Whichever max occurred first will trigger the purging of archive. Here you can see the content repository, and disk free space is 50% and archived content claims 15%, active content claims 35%. As an example, we can consider content repository interface. Defines the capabilities of a content repository. Append options are not available on the methods, but a merge capability is provided, which between that and creating new claims, a merge. As an example, we can consider IO exception as an example for an exception. This occurs if unable to init in initialize method in interface content. As an example too, we can consider property nifi.content.repository.directory.default strict. The location of the content repository. The default value is ./content_repository. Note multiple content repositories can be specified by using the nifi.content.repository.directory. Prefix with unique suffixes and separate paths as values. For example, to provide 2 additional locations to act as part of the content repository, a user could also specify additional properties with keys of nifi.content.repository.directory.content1 equal /repos/content1, nifi.content.repository.directory.content2 equal /repos/content2. Providing 3 total locations, including nifi.content.repository.directory.default. This property is available in nifi. As an error example, we can consider this one. Nothing is archived directory in content repository. This occurred in archive. Now we are focusing on Provenance Repository. The Provenance Repository is where all provenance event data is located. The repository construct is pluggable, with the default implementation being to use one or more physical disk volumes. Within each location, event data is in. Here you can see working with a FlowFile attributes is a core aspect of NiFi. It is assumed that attributes are small enough to be entirely read. entirely read into local memory every time the processor executes in it. So it is important that they are easy to work with, as attributes are the core way of routing and processing FlowFile. It is very common to have processors that just change the FlowFile attributes. One such example here is update attribute processor. All the update attribute processor does is change the incoming FlowFile's attributes. Taking a look at the diagram, before the processor, there is the FlowFile F1 that has attributes and a pointer to the content C1. The processor update FlowFile's attribute by creating a new delta F1.1 that still has a pointer to the content C1, and attributes underscore modified provenance event is emitted when in this example the previous processor invoke HTTP fetch the information from a URL and created a new response flow file within the file name attributes that is the same as the request flow file. This does not describe the response flow file, so the update attribute processor modifies the file name attribute to something more relevant, URL and transaction ID. For the sake of focusing on the attributes underscore modified event, the flow files F1 provenance events leading up to this point. In addition to additional arbitrary attributes via update attributes, extracting information from the content of a flow file into the attributes is a very common use case. One such example in the web crawler flow is the extract text processor. As an example, we can use URL when it is embedded within the content of the flow file. So we must extract the URL from the content of the flow file and place it as an attribute. This way we can use expression language to reference this attribute in the URL property of invoke HTTP in this example. Here you can see response is connected to update attribute, and update attribute interact with success before and after. Response is connected to update attribute interact with success, and if here in flow file before F1 is connected, if F1 is pointing to C1, and in content you can see C1. In after you can see F1.1 is connected is pointing to C1, and in content repository you can see C1, and in provenance here you can see the provenance repository stores the metadata and context information of each flow file. Every time a flow file is modified, NiFi takes a snapshot of the flow file and its content and its context at this point. The name for the snapshot in NiFi is provenance event. The provenance repository records the provenance events. Provenance enables us to retrace the lineage of the data and build the full chain of custody for every piece of information processed in NiFi. On top of offering the complete lineage of data, the Provenance Repository also offers a replay the data from any point in time. The difference between FlowFile Repository and Provenance. The idea behind the FlowFile Repository and Provenance Repository is quite similar, but they don't address the same issue. The FlowFile Repository is a log that contains only the latest state of the in-use flow files in the system. It is most recent picture of the flow and make it possible to recover from outage quickly. The Provenance Repository, on the other hand, is more exhaustive since it tracks the complete life cycle of every flow file that has been in the flow. If you have only the most recent picture of the system with the FlowFile repository, the Provenance repository gives you a collection of photos or video. You can rewind to any moment in the past to investigate data, replay operations from the given name. It provides complete lineage of data. Here you can see a process is interact with a snapshot. Snapshot is passed from process to Provenance repository here. As an example, we can consider Provenance event repository interface. This repository houses Provenance events. The repository is responsible for managing the life cycle of the events, providing access to the events that it has stored, and providing query capabilities against the events. As an example, as an exception example, we can consider IO exception. If error reading from repository in get events method in interface Provenance events repository. As an example 2, we can consider NiFi.provenance.repository.implementation. The Provenance repository implementation. The default value is org.apache.nifi.provenance.write-ahead Provenance repository. 3 additional repositories are available as well to store Provenance events in memory instead of on disk, in which case all events will be lost on restart and events will be evicted in a first in first out order. Set this property to org.apache.nifi.provenance.volatile Provenance repository. This leaves a configurable number of Provenance events in the Java heap, so the number of events that can be retained is very limited. The third and fourth options are available: org.apache.nifi.provenance.persistent Provenance repository and org.apache.nifi.provenance.encrypted write-ahead Provenance repository. The persistent Provenance repository was originally written with the simple goal of persisting Provenance events as they are generated and providing the ability to iterate over those events sequentially. Later, it was designed to be able to compress the data so that more data could be stored. After that, the ability to index and query the data was added. As requirements evolved over time, the repository kept changing without any major redesigns. When used in a NiFi instance that is responsible for processing large volumes of small flow files, the persistent Provenance repository can quickly become a bottleneck. The write-ahead Provenance repository was then written to provide the same capabilities as the persistent Provenance repository while providing far better performance. The write-ahead provenance repository was added in version 1.2.0 of NiFi. Since then, it has proven to be very stable and robust, and as such was made the default implementation. The persistent provenance repository is now considered deprecated and should no longer be used. If administering an instance of NiFi that is currently using the persistent provenance repository, it is highly recommended to upgrade to the write-ahead provenance repository. Doing so is simple as changing the implementation property value from org.apache.nifi.provenance.persistent provenance repository to org.apache.nifi.provenance.write-ahead provenance repository. Because the provenance repository is backward compatible, there will be no loss of data or functionality. The encrypted write-ahead provenance repository built upon the write-ahead provenance repository and ensures that data is encrypted at rest. Note: the write-ahead provenance repository will make use of the provenance data stored in the persistent provenance repository. However, the persistent provenance repository may not be able to read the data written by the write-ahead provenance repository. Therefore, once the provenance repository is changed to use write-ahead provenance repository, it cannot be changed back to the persistent provenance repository without deleting the data in the provenance repository. And this is available in NiFi properties file. As an example, we can consider this error. The format version is not supported. Resource buffered checksum index input. 3 needs to be between 7 and 9. This version of Lucene only support indexes created with release 6.0 and later. This error occurred in while upgraded Apache NiFi from 1.9.2 to 1.11.4. Now we are focusing on primary node. Every cluster has one primary node. On this mod, it is possible to run isolated processes. Zookeeper is used to automatically elect a primary node. If that node disconnects from the cluster for any reason, the primary node will automatically be elected. Users can determine which node is currently elected as the primary node by looking at the cluster management page of user interface. Here you can see the primary node. Here you can see its primary. Here we consider list HDFS and fetch. Here we are considering pulling. A different pulling scenario involves performing a listing operation on primary node. And distributing result across cluster via site to site to pull the data in parallel. This typically involves list and fetch processor, where the list processor produces instructions or tasks for the fetch processor to act on. An example of this scenario is shown in this diagram with list HDFS and fetched HDFS. List HDFS is scheduled to run on the primary node, and performs a directory listing, finding new files since the last time it executed. The results of the listing are then sent out list HDFS as flow files, where each flow files contain one file name to pull from HDFS. These flow files are then sent to the remote process group connected to an input port with in the same cluster. This causes each node in the cluster to receive a portion of files to fetch. Each fetch file processor then processor can then fetch the files from HDFS in parallel. Here you can see node 1 primary and node 2 list HDFS is connected to RPG here, and also HDFS here, and RPG is connected to input port in node 1 and input port in node 2. Input port is connected to fetch HDFS, and fetch HDFS is connected to HDFS. Here we can, as an example, we can consider some code segment used from package contains resource classes used by applications included in the platform and define the application permissions for the system failures. Here you can see the method which returns true if this instance is the primary node in the cluster, false otherwise. And here you can see leader election manager dot is leader is cluster roles dot primary node. As an example, we can consider these properties. NiFi.zookeeper.connect.string, NiFi.zookeeper.connect.timeout, NiFi.zookeeper.session.timeout, NiFi.zookeeper.root.not, NiFi.zookeeper.client.secure, NiFi.zookeeper.security-keys-store, NiFi.zookeeper.security.keystore-type, NiFi.zookeeper.security.keystore-password, NiFi.zookeeper.security.truststore, NiFi.zookeeper.security.truststore-type, NiFi.zookeeper.security.truststore-password, NiFi.zookeeper.jute.maxbuffer. NiFi depends on Apache Zookeeper for determining which node in the cluster should play the role of primary node and which node should play the role of cluster coordinator. These properties must be configured in order to NiFi to join. Now we are focusing on Zookeeper Client. Clients connect to a single Zookeeper server. The client maintains a TCP connection to which it sends requests, get responses, get watch events, and send heartbeats. If the TCP connection to the server breaks, the client will connect to a different server. Here you can see Zookeeper. Zookeeper is a distributed open source coordinating service for distributed applications. It exposes a simple set of primitives that distributed applications can build upon to implement higher level services by synchronization, configuration maintenance, and groups and naming. It is designed to be easy to program to and uses a data model styled after a familiar directory-free structure of file systems. It runs in Java and has bindings for both Java and C. Coordination services are notoriously hard to get right. They are especially prone to errors such as race conditions and deadlocks. The motivation behind Zookeeper is to relieve distributed applications the responsibility of implementing coordination services from scratch. Like the distributed processes it coordinates, Zookeeper itself is intended to be replicated over a series of hosts called ensemble. The servers that make up the Zookeeper service must all know about each other. They maintain an in-memory image of state along with the transaction logs and snapshots in a persistent store. As long as a majority of servers are available, Zookeeper service will be available. Clients connect to a single Zookeeper server. The client maintains a TCP connection through which it sends the request, get responses, gets watch event, and sends heartbeats. If the TCP connection to the server breaks, the client will connect to a different server. Here you can see a Zookeeper service here, and in the server there's a leader here, and you can see the servers here. This is connected to another server, this is connected to another server, and you can see client. Each client is connected to a server here. As an example, we can consider invalid client in Zookeeper state provider. And as another example, we can consider client port property. Zookeeper client port duplicated. Client port is no longer specified in a separate line as of NiFi 1.10.x. Default value is 2181. This is available in Zookeeper. As another example, we can consider NiFi.zookeeper.client.secure property. Whether to access Zookeeper using client TLS, default value is false, and this is available in NiFi.config NiFi.properties file in $NiFi._home/. As an error example, we can consider this one error. Background retry gave up org.apache.curator connection loss exception, and other information are available here. This occurred in a 3-node cluster, all using NiFi version NiFi 1.2.0.3.0.0.5. Now we are focusing on cluster coordinator. A NiFi cluster coordinator is the node in a NiFi cluster that is responsible for carrying out tasks to manage which nodes are allowed in the cluster and providing the most up-to-date flow to newly joining nodes. When a data flow manager manages a data flow in a cluster, they are able to do so through the user interface of any node in the cluster. Any change made is then replicated to all nodes in the we can As an example, we can consider NiFi.cluster.protocol.heartbeat.interval property. The interval at which nodes should emit heartbeats to the cluster coordinator. The default value is 5 seconds. This is in NiFi. As an error example, we can consider the segment of an error message here. You can see here checking if there is already a cluster coordinator elected. Now we are focusing on Zookeeper Server. The servers that make up the Zookeeper service must all know about each other. They maintain an in-memory image of state along with the transaction logs and snapshots in the persistent store. As long as the majority of the servers are available, the Zookeeper service will be available. You can see Zookeeper service here. I have already explained this Zookeeper service under Zookeeper Client. Here these clients connect to the Zookeeper server here, and these servers, the servers that make up the Zookeeper service must all know about each other. They maintain an in-memory image of state along with the transaction logs and snapshots in the persistent store. As long as the majority of the servers are available, the Zookeeper service must be available here. As an example, we can consider this property. NiFi.state.management.embedded.zookeeper.start specifies whether or not this instance of NiFi should run on embedded Zookeeper server. This is available in NiFi. As another example, we can consider this NiFi.state.management.embedded.zookeeper.start equal false, and NiFi.zookeeper.connect.string equal localhost : 2181, localhost : 2182, localhost : 2183. Configuring an external Zookeeper to work with Apache NiFi. Here, for two nodes, for a 2-node NiFi cluster, in each config directory, modify the following these properties in the NiFi properties file. The first property, configure NiFi to not to use its embedded Zookeeper. As a result, Zookeeper.properties and state-management XML files in the config directory are ignored. The second property must be specified to join the cluster, as it lists all the Zookeeper instances in resemble. This is the end of my presentation. Thank you very much for watching my